Welcome back. In this video, we look at clustering. Clustering is unsupervised because we either don't have labels for the data or choose to ignore them for the purpose of learning more about the data. The goal of clustering is to find groups within the data that share common features. Here we see the familiar iris data clustered into three groups. There are many clustering algorithms, but in this video we focus on two: kMeans clustering and hierarchical clustering. As in K and N, distance is a central concept in clustering. And also like K and N, scaling will be important. Imagine we're clustering people by their physical size. If they are 2 pounds different in weight, we would consider them similar, but not if they're 2 feet different in height. Scaling will put all predictors in the same measures. First, we look at kMeans clustering. In this notebook, we're going to cluster the iris data. The kMeans function is in R. We don't need to load a package. The first argument specifies the data you want to cluster. Here I'm only using petal length and width. And the second argument is the number of clusters you want. In this case, we have an advantage because we know that iris dataset has 3 classes. Normally, we don't have any idea how many clusters we want. The third argument is the number of starts. Because the algorithm starts with a random assignment, the algorithm is usually run several times with different random assignments. The kMeans algorithm will select the best clustering according to its internal metrics. We set a seed for reproducibility because of this initial random assignment. The iris cluster variable holds everything it learned about the clusters. When we print it out, we see that it found 3 clusters of size 52, 48, and 50, which means that we learned something real because we know that the actual 3 classes have 50 observations each. Here are our centroids, our cluster means, and then we have vectors of cluster assignments. The metric shown next is within cluster sum of squares by cluster. The sum of squares measures the variance of the observations within each cluster. A smaller sum of squares indicates a more compact cluster. Notice that this third cluster has a very small sum of squares metric, and the others are a bit larger. The other clusters are more spread out. Finally, the output just shows the components you could look at within the iris cluster object. There are many variations of the kMeans algorithm, but generally they follow this pattern. First, a random assignment to clusters is given, and then each observation is assigned to its closest centroid, or mean. Then the centroids are recalculated, and steps 2 and 3 are repeated until convergence. Convergence meaning that observations are no longer being assigned to different clusters. The metric that we saw was within sum of squares. So it measures the distance here of each point to its centroid. The centroid is essentially the mean. Those are squared and all of them sum together. The lower the within sum of squares, the more compact the cluster. kMeans is considered an example of the expectation maximization algorithm, EM. In the E step, each observation is assigned to the closest centroid. In the M step, the centroids are recomputed. EM is a heuristic approach that finds solutions where parameters cannot be directly calculated. Let's look at another example of kMeans. This notebook uses a wine dataset in package rattle. It contains 13 chemical measurements on 178 Italian wines. The first column type indicates 3 different wine varieties. We'll drop this variable for the clustering. This function will plot the within sum of squared errors versus the number of clusters. We're going to try number of clusters from 2 to 15, setting a seed for reproducibility, and calculating the within sum of squared errors. And this plot shows that metric by number of clusters. What you want to look for in a plot like this is something like an elbow. It's always the case that the more clusters you have, the lower your within sum of squared errors. But you want an optimal value somewhere around this elbow, and this is one way to find that. Another way is to use a function in library nbclust. Here, we're telling it to look from 2 clusters up to 15 on kMeans. It will go through almost 30 different metrics and take an aggregate vote on what's the best number of clusters. In this case, there's a strong preference for 3 clusters. Then we run kMeans on our dataset using the 3 recommended clusters. If we look at the clusters compared to the actual type of wine, we see that there is a strong correlation here. So the algorithm is really learning something important in the data. There are dozens of clustering metrics, but one that's commonly used is the RAND index, which is a measure of cluster purity that ranges from -1 to +1. Here it's very close to 0.9, so that indicates a very good clustering of the data. Let's look at an example on some synthetic data, just some made-up data. I created 3 distributions with the rnorm function, specified what their centers would be, and made the data a little bit messy so that it would overlap a little. Here we're plotting it with shapes for the 3 distributions, the squares, the circles, and the triangles. Let's try the kMeans algorithm with only one iteration. We can specify that here with this parameter itermax, and only one start. Not something that we would normally do, we just wanted to get the algorithm's first impression of the data. And we see it put this square over with the orange, and it put these 3 dots over with the purple triangles here. Letting it run for unlimited iterations by taking that parameter out, and again only one start, we see that nothing really changed. In fact, it only ran 2 iterations before convergence. Let's try k equals 2, k equals 4, and k equals 5. And then print out the within sum of squares for all of these different numbers of clusters. And what you see is that a sharp drop here between k equals 2 and k equals 3, and then it diminishes as you go up to the larger number of clusters. And again, remember that the within sum of squares will always go down with more clusters. Here is that function we use to find the optimal k, and we see that our elbow here is at 3. Putting all the criteria again, it recommended 3 clusters. The next clustering algorithm we look at is hierarchical clustering. There are many variations of this algorithm as well. Here's the algorithm for what's called bottom-up clustering. Hierarchical clustering produces this graph over here on the right called a dendrogram. The first step is that each observation is placed in its own cluster. Then the distance between all clusters is calculated, and the 2 closest clusters are combined. For example, these 2 are combined. In this process of steps 2 and 3 are repeated until convergence, which in this case means that everything is in one big cluster. In calculating the distance between clusters, there's different ways to do that are called linkage. Single linkage is the shortest distance between any 2 points in a clusters, and that tends to create elongated clusters. Complete linkage is the longest distance. That tends to create more compact clusters, but it's sensitive to outliers. The average linkage just uses average distances. The disadvantage of hierarchical clustering is that it's a greedy algorithm. Once an observation is there, it's stuck. It doesn't try several starts like kMeans does, and it can really bog down in large data. What we can do after clustering is to cut the dendrograms in different locations. So here, this purplish line, we've cut it so that we have 2 clusters. This orange line would give us 3 clusters, and the green line would give us 4 clusters, and so on. Let's look at a small example in R. In this notebook, we're looking at a nutrient data set in package FlexClust. It has 5 nutrients: energy, protein, fat, calcium, and iron, for 27 different prepackaged foods. First, we scale the data, and then to do the clustering, we use the R built-in distance function. This will calculate Euclidean distance between each of the 27 different food types using average linkage. And then we plot our dendrogram. Trying to make sense of these is a little tough. Here it clustered bluefish and chicken, and here it clustered tuna and chicken. Here it did cluster 2 canned fish items, and also here. So it is a little bit hard to understand what it learned from the data. You can cut the dendrogram with a built-in cut tree function, and we're trying different cuts from 3 to 11. Most of the algorithms we study are supervised, so it may not be obvious why unsupervised learning is useful. Sometimes the goal is just to learn more about the data by finding similarities. Clustering is ideal for learning about raw data. Other uses are anomaly detection to detect unusual data points. A field called associate mining identifies things that occur together. An example of this is discovering what items people buy together. You'll notice that when you buy something online, you get suggestions of other things you might like. A story I once heard about this is that Walmart discovered that beer and diapers were bought together late at night, so they started stacking cases of beer near the diaper aisle. And the speculation was that when dads are sent out late at night to Walmart to get diapers, they pick up a little something for themselves as well. We won't look at many more unsupervised algorithms. In the next video, we look at decision trees, a supervised algorithm.